In lecture 16 of Symmetries, Particles and Fields, we're going to start off by proving some facts about the simple roots that we introduced at the end of last lecture. These we'll prove are linearly independent and various other facts about them. This will lead us to the definition of something called the Cartan Matrix, and we'll rewrite the Lie algebra in terms of this Cartan Matrix yet again. So it turns out that different Lie algebras of simple finite dimensional compact groups are distinguished by having different Cartan matrices and different ranks. So by looking at the properties of the different Cartan matrices, it turns out one can classify all of the simple complex Lie algebras of compact groups. So what we're going to do is indicate how this works in the sort of simplest case. We're not going to prove the Cartan Classification Theorem in general, but we will give you the results of all the different possible Lie algebras by the end of the lecture. So let's start with more properties of roots. So we're going to prove 6 things here. Some of them are purely about simple roots. So for example, the first one is if we take 2 simple roots. So remember, the set of simple roots is called phi s. So we take any 2 alpha and beta in phi s, then the difference of them is not a root. So it's not, the difference isn't in the root set. So to prove this, let's suppose the opposite and then prove a contradiction. So let's suppose that alpha minus beta is in the root set. So alpha minus beta has to be either be a positive root or a negative root, and we're going to cover each case in turn. So if it's a positive root, in other words, alpha minus beta is in phi plus, the set of positive roots. So what this means is that we can rewrite alpha as alpha minus beta plus beta. Okay, and so if alpha minus beta is a positive root, then alpha has been written as the sum of 2 positive roots. Therefore, alpha isn't simple because simple roots can't be written as the sum of 2 others. But this contradicts our initial assertion that both alpha and beta are simple roots. So that's a contradiction. And the argument the other way, let's suppose alpha minus beta is a negative root. Well, we basically just work it in a very similar manner. That means that beta minus alpha is a positive root. So we can just turn the argument around and say that beta, which is beta minus alpha plus alpha, and again, beta minus alpha is a positive root, alpha is a positive root. So beta is the sum of 2 positive roots, therefore it can't be a simple root. Again, that's contradictory to our initial assertion that they're both simple roots. Okay. Secondly, we're going to define something called a length of a string now. So let's take the length. So this is written L alpha comma beta suffix of, so we have this alpha string through beta, which was this set of vectors S alpha comma beta. So remember, this is the alpha string through beta. So we're calling the length L alpha beta, and it's just the number of elements in S alpha comma beta. So we're going to show now that L alpha comma beta is equal to, well, it's got to be a natural number because it's a number of elements, and it's minus, we're going to show that it's 1 minus twice the inner product between alpha and beta over the inner product of alpha with itself. And we're going to, and that has to be a natural number. So let's recall our definition of the alpha string through beta from the start of, well, maybe it was the end of the penultimate lecture. So we've shown actually last time that our definition is equivalent to this. So we take some integer times alpha and add it to beta, where this integer is between these numbers n plus and n minus, which we defined last lecture, where n plus is bigger than or equal to 0, and n minus is less than or equal to 0. Last time we derived that the sum of them, n plus plus n minus, is equal to -2 alpha inner product with beta over the inner product of alpha with itself. And this is, of course, an integer. So if you think about it, this property 1 says that we're not allowed to subtract any of the roots, any of the positive roots off each other, and still end up with a root in the root set. Oh, beg your pardon, 1 second. So now, yeah, sorry, I should have said. So we take alpha and beta as simple roots. Okay. So yes, given that these are simple roots, we're not allowed to do any subtracting, and so n minus has to be 0. So if we substitute that into the previous equation, we get this, -2 alpha comma beta over alpha alpha. All right, so actually this equation here comes from, I think I wrote it as 6.8. So all that remains now is to substitute, is to work out what the length of alpha comma beta is. Well, we can, in general, we can, add on n plus times alpha to the set. So that gives us n plus options. We can subtract n minus alpha times alpha in general, but we haven't counted the root beta, which is another element of the set. So we have +1. And now we substitute in for n plus and n minus, and we get the assertion that we had in the beginning. Okay, good. So let's just look at this for a second. Now, if you look at this thing, if we take alpha not equal to beta, then what we have is that this quantity here has to be a natural number that's bigger than or equal to 0. And the only way to arrange for this expression to be bigger than or equal to 0 is if the inner product between alpha and beta is less than or equal to 0, because the denominator is positive because we have a Euclidean inner product. So the third property is that if alpha and beta are simple roots and alpha is not equal to beta, then this implies that alpha comma beta is less than or equal to 0. So this is just a corollary of property 2. So the fourth assertion is that any positive root beta can be written as a linear combination of the simple roots. With positive coefficients. I should say positive integer coefficients. Okay, so let's consider what this positive root could be. Well, it could be, it might be a simple root or it might not. So let's take the simple root case first. So if beta is a simple root, well, then it is a linear combination. It's just we have 0 for all the other integer coefficients and +1 for the beta. So it's got a positive integer coefficient. So we're done. If beta isn't a simple root, then what you can do is just write what this means is it must be able to be written as the sum of two positive roots by definition of a simple root. So for some positive roots, beta 1 and beta 2. Now, since our rank is finite, we can carry on iterating until all of and you just iterate this until you get down to simple roots, basically. So in other words, we use the same argument for beta 1. We can split that up into two other roots, unless it's a simple root, in which case we stop. We just carry on doing that for each term. Fifthly, so okay, so we've shown that a positive root can be written as a linear combination of simple roots with positive integer coefficients, but actually the fifth assertion says that all roots, let's call alpha in the root set, can be written as some linear combination of the simple roots where the coefficients are integers. So alpha I are simple roots. It's in the simple root set. So the simple root, so what this means, of course, is that the simple roots span our dual space to the Cartan algebra. So actually, this is just a corollary of 4, because we can write the negative roots as minus a positive root. Corollary of property 4. Okay, lastly, simple roots are linearly independent. So for this, let's consider all vectors in our dual space to the Cartan subalgebra. Okay, so now we use property 5. So we can write lambda as some coefficients times alpha I, where now the coefficients are real and alpha I are simple roots. And I'm going to make it clear that we're talking about, okay, so there's a difference between simple roots and simple Lie algebras, but we're going to restrict to the case of simple Lie algebras, okay? So all right, so okay, we've got this expansion of any vector in this dual vector space. And now let's also restrict to the case where we haven't got a zero vector, basically. Not all of these CIs are zero. So we let J plus are the set of all i's such that Ci is bigger than 0, and J minus is the set of all i's such that Ci is less than 0. And we define, so these are definitions actually. Lambda plus or minus to be plus or minus I in J plus or minus Ci alpha I. Okay, so we have some positive coefficients, we have some negative ones, and we can see that this initial lambda is just lambda plus minus lambda minus. So this implies, if we consider the inner product of lambda with itself, we just expand out this difference squared. So we get two terms which we know are positive. And then we get minus twice lambda minus lambda plus. There's only one extra term because of the symmetricity of the inner product. Okay, that's fine. So these two, from the Euclidean nature of the inner product, these two first terms are positive. So this right-hand side is bigger than minus 2 lambda minus lambda plus. If I write this down again, I just substitute back in for lambda plus and minus. And you know what this inner product is defined to be. We get plus 2 sum I in J plus, sum J in J minus, Ci Cj, alpha I, comma, alpha J. Now, all right, so we can say something about the sign of these things. All right, so Ci Cj, remember the j's are always negative and the i's are always positive, so this is always less than 0. And property 3 actually tells us that this is less than or equal to 0. But for simple, the algebras, it has to be less than 0. So it's only semi-simple case really where we get the equality. Well, it is only the semi-simple case. Okay, so what we have is that the inner product of lambda with itself is bigger than 0 unless lambda itself is 0. Or in other words, so I should say that this right-hand side then we've just shown is, okay, maybe that's less. So the whole thing, because it's the multiple of a negative number and another negative number is bigger than or equal to bigger than 0. And so the inner product of lambda with itself is equal to 0. And this is, of course, this should have no solutions apart from lambda equal to 0. Implies that Ci is 0 if and only if Ci is 0 for all I. Therefore, simple roots are linearly independent. Okay, we have one more property, property 7. Property 7 is that there exactly are simple roots. So remember, this is the rank of the Lie algebra. So we've shown that the simple roots are linearly independent by property 6. And property 5 tells us that we can expand any roots in terms of the simple roots and integer coefficients. So that means that, so the simple roots span this dual space, and so therefore the simple roots are a basis by both of those properties. Simple roots are a basis for the dual space to the Cartan subalgebra. So therefore, the size of this set of the simple roots is the dimension of our dual space. And this, of course, is R. The real dimension is R. All right, good. So we're now going to define the Cartan matrix. Of a Lie algebra. So this is an R by R matrix. With elements Aij is equal to twice alpha I comma alpha j over alpha j comma alpha j. So alpha I and alpha j are the simple roots. So remember, we proved before this is this quantity here is an integer. So this is a matrix of integers. Now notice it's not necessarily symmetric because this alpha j on the bottom breaks the symmetry. Under switching I and j. All right, so now we're going to rewrite the Lie algebra one last time. So we're going to, it's only a minor change of notation actually. So now, I'm going to define little h suffix I is h corresponding to the ith simple root, and e I plus or minus, this is going to be defined to be what we called before e with plus or minus alpha I, where alpha I is a simple root. So we have this new basis, notation for the basis really. Then if you look and see what our Lie algebra now, how our Lie algebra now reads, it's particularly simple. So we have that hi bracket with ei plus or minus without any sum on I is plus or minus twice ei plus or minus, no sum. So yeah, on I. So in other words, you know, the i's are the same index. That's all that means throughout the equation. We have that hi and ej plus or minus is plus or minus aji ej plus or minus, and there's no sum on j in this equation. All I've done, if you look at the Lie algebra, you'll see that you have this expression on the right hand side with I and j swapped, and so I've just substituted into the Cartan matrix element. And we also have that ei plus and ei minus, Lie bracket is hi. Again, no sum on I. And all other brackets are 0. All right, good. So this is a particularly simple form. And actually, it's interesting because what you see from this form of the Lie algebra is that the things that distinguish between our Lie algebras are firstly, you know, the rank, which determines how many of these operators that we have, you know, the values that I and j can range over. So that's one thing. But the other thing, the only other thing that distinguishes them is this Cartan matrix. So we see that the Lie algebras of simple groups are distinguished from each other by different Cartan matrices or can be distinguished, I should say, can be. If they have a different Cartan matrix but the same rank, they would be a different Lie algebra. Different Cartan matrices as well as their rank. Okay, so we're now going to go through a classification of the groups or the Lie algebras corresponding to the groups. So this is really Cartan classification. So, okay, and this is really a classification of finite dimensional complex simple Lie algebras. complex simple Lie algebras. Let's give all the caveat, all the specializations of compact groups. So this has 2 steps. Firstly, we classify all Cartan matrices. And secondly, show that Cartan matrix uniquely determines each Lie algebra. All right, so as I mentioned at the start, we're not going to prove the Cartan classification. It would take quite a few lectures to do so. But what we're going to sort of play around at the easy end of it. We can see how it could kind of come out. So let's examine the Cartan matrix properties. So just from its definition, if you, let's go up and look at the definition, where is it? So if we put I equal to j with no sum, we just get 2. So the diagonal entries of it are 2. So that's just from the definition. Now, also from the definition, remember we have symmetry of the inner product. So if Aij happens to be 0, then by symmetry, it doesn't matter if the denominator is different but non-zero. Then we'll also get 0 for Aji. So Aij is 0 implies Aji is 0 by symmetricity of the inner product. So remember, when we had, so property 3 that we proved just now was that when you have the inner product between two different simple roots, the inner product is less than or equal to 0 for alpha not equal to beta, but then both simple roots. So this implies, okay, so if you look at it again, this implies, so we get some, this is less than or equal to 0. So we know that the denominator is positive. So we must have, we must be in the negative integers for the elements, the off-diagonal elements of this matrix. In other words, Aij is in minus, okay, natural numbers. You can have 0 for all I. No, I not equal to j, so off diagonal. So it's a fact, and I'll show you how to prove it in case you've forgotten, that the Euclidean inner product implies that the determinant of the Cartan matrix is positive. All right, So our Euclidean inner product, of course, means let's take a non-zero vector lambda. So this means lambda is expanded in terms of these simple roots. So we have lambda I, alpha I. So here we do have a sum on I, alpha j, lambda j. So we can divide this by alpha j, multiply by 2 and divide by the inner product of alpha j with itself. And so this implies, by doing that, we see that lambda I times the Cartan matrix times lambda j is bigger than 0. So now we do have some on I and j. So let's just consider this for a moment. Let's just write it. It's easier if we just write it in matrix form. So if we, what this means is that, I mean, lambda is just some non-zero vector. So what this means really in matrix form is that lambda, let's write it in terms of just some vector x. X transposed A x is bigger than 0 for all x, okay? Now, if we consider an eigenvector of A, so that, in other words, A xi is Li xi. If I substitute this in to the previous inequality, what I get is that Li xi transposed xi. Okay, no, this is no sum on I. No sum. So the previous inequality tells me that that's greater than 0. But this, the Euclidean inner product tells us that this combination is 0. So all of the eigenvalues must be bigger than 0. And we can write the determinant as the product of the eigenvalues. So I should have said that this is the proof. Okay, so taking this case of simple Lie algebras, this means that A is not reducible. It's not in block diagonal form. Okay, let's take an example, simplest example. Rank 2. So here, we remember we have a 2 by 2 matrix to the Cartan matrix. We have 2's down the diagonal, and we have minus m and minus n on the off diagonals, where m and n now are natural numbers. So we have this constraint that the determinant has to be bigger than 0. And the determinant of this is 4 minus mn. That must be bigger than 0. And so the distinct cases for m and n, well, they could be 1 and 1, 1 and 2, 1 and 3. but that's it. Otherwise, if you have 2 and 3, you get a negative determinant. So we're not interested in cases where we just switch, basically switch the labeling of these vectors. They're not distinct cases, because that's just changing, it's just switching, it's permuting the simple roots, which is just a relabeling. Okay. So that's it. I mean, so already this shows you that you can only have 3 Lie algebras of rank 2 groups, and we're going to see that come out in a second. So it can also be shown that the product of Aij with Aj has to be 0, 1, 2, or 3. Without a sum. And that you can have at most 2 distinct lengths in a simple Lie algebra. So a complexified Lie algebra can have roots of at most 2 distinct lengths. We're not going to show these properties. Right. So now we're going to go on to on a way of representing these different possibilities. So each distinct diagram corresponds to a distinct Lie algebra, and these are named after Dinkin. So these are called Dinkin diagrams. So these represent the Lie algebra in a simple way. So what we do is we draw a node, which to you and me is a little circle, for each simple root. And then you join the nodes of alpha I and alpha j with maximum of size of Aij and the size of Aji, modulus. So remember, we said above that you can show that this is going to be 0, 1, 2, or 3 lines. And in the case where we have 2 or 3, connecting 2 nodes, draw an arrowhead pointing to the shortest. So if we have that the off-diagonal element is -1, let's see if I can find it, yeah, then you can show by this formula that the length of the 2 nodes is the same. But if it's -2 or -3, you can show that one's longer than the other. So remember, for rank 2, we have these 3 different cases. we showed that there exists 3 different possible Cartan matrices and associated Dinkin diagrams. So we have this one. So this is just represented by 2 nodes with a single line between them. We can have this. Again, we have 2 nodes, but now we have 2 lines between them, and there's an arrow pointing to the shortest node, shortest simple root, or we can have the following. All right, so in order to prove the Cartan classification theorem, you basically extend all of these arguments about the possible forms for the Cartan matrix. But we also extend to the semi-simple case, we extend Dinkin diagrams to the semi-simple case by no connection. So if two elements of the simple roots, 2 of the simple roots commute, then you just have no connection between them. So let's write the results of the Cartan classification theorem. Again, we haven't proved it. So what we're going to do is write all finite dimensional, complex, simple Lie algebras of compact groups. Now, all right. Let me do it on the next page. So we have the diagram. We have the physics notation for the algebra. We have the maths notation, and we have a comment. So, all right. So notice that these 2 diagrams I've just drawn are they are distinct, because in one the arrow points out of the diagram, and in the other one it points into the diagram. So they do correspond to distinct Lie algebras. Now, the idea is there are R nodes here, and R can be 1 up to. Oh, actually, let's call this n equals R. So n goes from 1 up to infinity nodes. And these 4 are examples of what are called the, so these are 4 infinite series, an infinite sequences of what are called classical Lie groups. Okay, so the maths notation is simple. It's AN, BN, CN, DN for these. The physics notation is okay, so this is let me see. This is the complex Lie algebra of SU n plus 1. This complex Lie algebra of SO 2n plus 1. This is the symplectic group 2n. And this is the complex Lie algebra of SO 2n. Sorry, that's SP and SO 2n, yes. Note, okay, well, I'll define that in a second. Then there are some exceptional Lie algebras, E6, E7, E8, F4, and G2. And actually, I mean, okay, so what I'm really labeling here is the maths notation for the group G. And so we just have, you know, Lie algebra of E6, etc. All right, now this one looks like 2, 4, 5, and this looks like the same thing, but with a node stuck on the end. So you'll notice that in the maths notation, the suffix is the number of nodes. So there's only one Lie algebra in this classification with 3 lines, and that's this G2 exceptional Lie algebra. Now, there's one thing to notice. You can ask what D2 is. D2 is defined the Dinkin diagram is defined to be, so the diagram of D2 is defined to be just this. So this represents the Lie algebra of SO4. Now, you can notice some isomorphisms by the fact that the Lie algebras have identical diagrams. So you'll see that A1, B1, and C1 are identical. By definition, D1 doesn't exist. So from that, you can see, so, you know, if we look and see what that means for the Lie algebras in our physics notation, we see that the Lie algebra of SU2 is the same as that of SO3. And it's the same as SP2. Well, I should really say that it's isomorphic, actually. So the Lie algebra of SO5 is isomorphic to the Lie algebra of SP4. So if we look, if we only have two nodes here, then of course it's just by switching the two nodes we get this isomorphism. Okay, that's it for this time. Next we'll look and see how we can derive something similar, which is maximal subalgebras. Not derive, but it's a mnemonic really for working out which maximal subalgebras we can have in our Lie algebras.